Welcome to the video on intermolecular forces or intermolecular interactions. When we look at the molecule of water and compare it to the molecule of methane, water is a liquid at room temperature and methane is a gas. This is the case because of intermolecular forces. So when water hangs out with other molecules of water, they have a strong force of attraction between those molecules. And that allows for them to stick together more tightly, which, as we talked about in the states of matter video, means that they are going to be more likely in the liquid state. Whereas in methane, when you have one methane molecule next to another methane molecule, they do have attractive forces, but it is not nearly to the extent of that of water. And in this chapter, we will talk about the different intermolecular forces that exist between molecules. Water has stronger intermolecular forces than methane. Water is polar. If we can recall back when we talked about Lewis dot structures and polarity, remember the hydrogens are partial positive and that oxygen is partial negative. And so in each case, we have this kind of dipole that happens. And then if we think about the molecule as a whole, we would say this does have a dipole, and the overall dipole looks like this. Whereas in methane, because hydrogen and carbon have very similar electronegativities, those electrons and those bonds there in methane are shared equally. And so we call that nonpolar covalent, and then this molecule itself would be nonpolar. So the intermolecular forces depends very much on the polarity of the molecule that we're talking about. So water has a dipole, and so those water molecules attract each other more prevalently than methane. Methane is nonpolar, there is no dipole, and so it does not have the same kind of attraction. And that is why methane exists in the gaseous form, because the intermolecular forces are weaker. Those molecules are more spread out in the gas phase. I'd like to introduce the difference between inter and intramolecular forces. Intermolecular forces are the ones that we were just talking about. Those forces exist between molecules. So you have two water molecules, and we're talking about the way that they interact with each other. They influence the physical properties of the substance. They influence whether the molecule is in a gas phase, a liquid phase, or a solid phase. Alternatively, we have intramolecular forces. And intramolecular forces exist within a molecule. This is the bonding. This is the sharing of electrons within a chemical bond. So intramolecular forces influence the chemical properties and the chemical reaction that had to happen in order to create that molecule or to break that molecule. Another way we can distinguish these or describe these intramolecular forces are bonding forces, and intermolecular are non-bonding forces. If we think about intra versus intermolecular forces in water, when we boil water, it goes from the liquid to the gas phase. We heat up the water and make it boil, and so then the water molecules go into the gas phase. So when we add energy, we can disrupt the intermolecular interactions that are happening between the water molecules, giving them enough energy to break apart and spread out. So when we boil water, we are not making and breaking chemical bonds. We are disrupting the intermolecular attraction between those molecules. If we wanted to break a bond, we would need to put much more energy in. If you look down here, in order to take water from liquid to a gas, we're talking about 44 kilojoules per mole. And if we want to actually break up the bonds in water to bring it to hydrogen and oxygen, we're going to need 940 kilojoules per mole. So there's a lot more energy required to break chemical bonds, not as much required for us to disrupt intermolecular interactions. What are the three main types of intermolecular interactions? The first is London dispersion forces, and this is temporary and or induced dipoles. These are very weak, and they happen with molecules that are non-polar. Second, we have permanent dipole forces. This is a stronger interaction, and it exists between two molecules that each have their own dipole. So we already have unequal sharing of electrons in a bond, and then we have this attractive force between two of these molecules. And third and strongest is hydrogen bonds, which is a very specific type of dipole-dipole. In this case, the strength increases considerably. This very specific dipole-dipole interaction exists only when we have nitrogen, oxygen, and fluorine bound to a hydrogen. We'll talk about each of these in more detail as we move forward. Remember, the order in strength is the weakest is London dispersion, the middle is dipole-dipole, and the strongest is hydrogen bonds. A little bit more about dispersion forces. Dispersion forces are weak and they exist in non-polar molecules. How dispersion forces happen is that we have an induced uneven distribution of charge by temporarily shifting the locations of electrons within a nonpolar covalent bond. We have this temporary dipole that then induces a temporary dipole in the molecule next to it, and then the molecule next to that, and then the molecule next to that, and so on and so forth. When we have this temporary dipole in a molecule, this intermolecular interaction increases as the number of electrons in our system increases. So the larger the molecule gets, the more electrons it has, the more of an induced dipole we can have. So the stronger the force. So as molar mass increases, so does dispersion forces. And if we look at this table, we can see that as we increase in molar mass, so as we go down the periodic table, fluorine, chlorine, bromine, iodine, we see the molar mass increases as expected, and also the boiling point increases. So as we get larger, we have greater surface area, and that surface area allows for greater interaction, therefore raising the boiling point or the energy needed to break them from the liquid into the gas phase. The same is observed as we continue to add carbons to our molecule. Hydrocarbon molecules are all nonpolar. As we increase in molar mass here, we also see an increase in the boiling point, meaning again that it takes more energy to break it from the liquid to go into the gas phase. As the molar mass increases, so does the London dispersion forces and the boiling points as well. Another little note about dispersion forces is that the structure of the compound affects the way that we can have this intermolecular interaction. So basically, the shape of the molecule will affect its surface area, and an increased surface area means increased intermolecular interactions. Cyclic molecules have the most interaction, and that's because they are stackable. So you can kind of pile them on top of each other just like this. Linear molecules also have a decent amount of interaction because some of these bonds are flexible and can rotate. They have more degrees of freedom, and so they can't stack maybe quite as well as these cyclic molecules. And so we have a little bit less interaction in that case. And then finally, when we have branched molecules, as shown over here, those do not stack very well at all. And so we have a much less interaction because of the decreased surface area. And then ultimately, we also have a lower boiling point. Moving on to dipole-dipole forces, remember that's going to be a little bit stronger than the dispersion forces. So this is an additional force that nonpolar molecules do not have. And this is based on the fact that we already have a dipole in our molecule. So we have a polar covalent bond in our molecule that is going to increase the intermolecular forces because it's no longer temporary. This is a permanent dipole. And so once we have the dipole capability in our molecules, as they stack together, they're going to organize it so that the energy stability is maximized. And so they are going to put their positive of one end next to the negative of the other, almost like a magnet you can think about. And that's a positive interaction. And so that's going to cause those two to be attracted to each other. These forces, however, you need to be aware, are very weak compared to covalent bonds. The strength of these dipole-dipole intermolecular interactions increase as the polarity of the molecule increases. So, in summary, the dipole-dipole forces are an attractive force that exists between polar molecules. And here's a schematic of what it may look like in a solid and what it may look like in a liquid. We can use these electron density maps to look at the polarity of our molecule. In this case, the color of red means that it has electron density and it's partial negative, and the blue means that there's less electron density, more positive. And so this would be a partial negative and a partial positive. So anytime you have two atoms next to each other that have a difference in electron negativity, then we have this dipole set up, and then we have this capability of having dipole-dipole interactions. And the last one I want to talk about is called hydrogen bonding. Hydrogen bonding is a very special type of dipole-dipole interaction that is considerably stronger. And this happens when we have nitrogen, oxygen, and fluorine with a hydrogen attached. You'll see some sample couple pictures here. So in this case, the lone pair on the nitrogen interacts constructively with the proton that's on the F. In the second case, the lone pair on the oxygen interacts constructively with the proton that's on the nitrogen. And lastly, the lone pair on the fluorine interacts constructively with the proton that's on the oxygen. So NOF, those are all going to be atoms. When they're covalently bound to hydrogen, are capable of having this hydrogen bond interaction. The hydrogen that's bound to the NOF is called the hydrogen bond donor, and the lone pair on the other molecule is going to be called the hydrogen bond acceptor. In this diagram, you can see the hydrogen bond is here, here, and here. So if we look at some of the trends in intermolecular forces, if we look at this plot with increasing boiling point on the y-axis plotted against the period of the periodic table as we go down the periodic table. So of course, as we go down the periodic table, we see an overall trend that increases boiling point. And that makes sense because as molecular weight or molar mass increases, we have an increased surface area, therefore an increased intermolecular interaction, therefore an increase in boiling point. So that makes sense. The three compounds that I want to highlight that are clearly out of the trend or deviant of the trend are water, HF, and NH3. And the three of those compounds have considerably higher boiling points, and that is because of hydrogen bonding. Remember, I said NOF. So these compounds are capable of hydrogen bonding, and they therefore have an unusually high boiling point because that intermolecular interaction of the hydrogen bond makes it much stronger interaction. So we have to use an elevated temperature to break those compounds out of the liquid phase into the gas phase where they can spread out. So in summary, hydrogen, when it's bound to oxygen, fluorine, and nitrogen, have a much higher boiling point. And this table shows that in general, as molar mass increases, so does the boiling point, except for NOF. If we were to do a couple practice problems, what types of intermolecular forces? You may also see that written as IMF, intermolecular forces. So if we look at H and Br, the first thing we think about is that a polar bond? And yes, it is a polar bond. And so we have a partial negative and a partial positive there. And so this one would have dipole-dipole. Now, it also has dispersion. Everything has dispersion. And then some molecules also have a dipole-dipole. And then other molecules also have hydrogen bonding. F2, so if we draw that compound out, F2, that is a non-polar covalent bond. So there's no dipole-dipole, but we are always going to have dispersion. And so if we skip down and we do NH3, if we draw out the Lewis dot structure of NH3, it looks like this. Each one of those bonds does have a dipole that goes towards the nitrogen. And so we have an overall dipole. Those are the lone pairs as well. It goes in that direction. And so this molecule does have a dipole. So in this one, we have dispersion, we have dipole-dipole, and then the last thing we look, okay, does this molecule have an NOF connected to a hydrogen? And the answer is yes. We have an N connected to a hydrogen, and so this molecule also has hydrogen bonding. We will do the rest of these problems in class. Now, if we think about liquids in general, we need to think about properties of liquids. The properties that we're going to discuss for the rest of this video are vapor pressure, boiling point, viscosity, surface tension, and capillary action. The general trend is that we have stronger intermolecular forces when we have lower vapor pressure, higher boiling point, higher viscosity, higher surface tension, and higher capillary action. So the only one that is the opposite direction is the vapor pressure. But when we have stronger intermolecular forces, that means that the molecule is going to have a higher boiling point, a higher viscosity, a higher surface tension, and higher capillary action, but lower vapor pressure. What is vapor pressure? It is the pressure exerted by the vapor on the liquid. So when we have this situation where we have things going from gas to liquid and liquid to gas and back and forth, it's the pressure exerted on the liquid by the vapor. A liquid's vapor pressure is directly related to the intermolecular forces present in the molecules. The stronger these forces, the lower the rate of evaporation, and therefore the lower the vapor pressure. We also have the term dynamic equilibrium, and this happens when we have the rate of the condensation, so going from gas to liquid, equal the rate of evaporation, so going from liquid to gas. And it turns out, and this will help us in the next conversation, the temperature at which the rate of condensation and the rate of evaporation are the same is known as the boiling point, or coming back from the gas to the liquid, it's known as the condensation point. But we will most likely be referring to it as the boiling point. There are some practice problems on the next slide that we'll do in class. Okay, so we just talked about boiling point. So boiling point is not just a surface process. It involves the entire liquid. And boiling point is the temperature at which the vapor pressure is equal to the surrounding pressure. And the normal boiling point is the temperature at which the liquid boils at a pressure of 1 atmosphere. So it turns out that as the surrounding pressure decreases, the boiling point decreases. Think about up on a mountain. And the opposite, in a pressure cooker, if we increase the pressure, the boiling point increases. And so now we end up cooking our foods at a higher temperature, and therefore we can eat sooner. And it turns out we get some insight on the pasta box and on the brownie box when you're reading how to make those things. A little bit more about boiling point in terms of intermolecular interactions. So if we have a hydrocarbon, that means just hydrogen and carbon, that is 5 carbons long, it makes this zigzag shape, and it looks like this. If we have those same 5 carbons, where the middle carbon has 4 carbons coming off of it, that compound right there looks more like a ball. And so if we look at the boiling point of these 2 compounds, the straight chain has a higher boiling point because those can pack tighter. And so we have an increased surface area. If we look at the one on the right here, it's more like a ball. And so that surface area is much smaller. And so the higher the surface area between the molecules when they are packing increases the intermolecular interaction, and therefore increases the boiling point. And the same happens as we go down the periodic table. Viscosity is the measure of the resistance to flow. The best example is maple syrup versus water. So maple syrup has a much higher viscosity. It's thicker and it flows much slower, and it's goopy and it's sticky. And so when we talk about something with a high viscosity, we are talking about a thick liquid that flows less easily. Viscosity depends on the intermolecular interactions, and it is related to the ease with which molecules can move past each other. Viscosity increases with stronger intermolecular forces. Please note that molecules are hard to move when they have strong intermolecular interactions. So a strong intermolecular force is going to have a large viscosity. Larger molecules have a larger viscosity. And next, I want to talk about surface tension, is the measure of the energy per unit area on the surface of a liquid. So stronger intermolecular forces lead to more stability and larger surface tension. It can also be described as the tendency of a liquid surface to shrink into the minimum surface area as possible. So the water will form these beads or these balls when it's on a surface like your windshield. They hold into their little balls and they want to be away from the glass and they want to be close to each other. That's the surface tension we're talking about. So to maximize hydrogen bonds, water forms these spherical shapes to minimize the surface area. Bugs also have this on the surface of a liquid. The last property of a liquid that I'd like to talk about is capillary action. And capillary action is the effect at which we see water crawl up the sides of a thin tube, or say up a paper towel, even though it might be going against gravity. There's 2 types of forces that exist here, and one is called cohesive forces. And cohesive forces exist when we're talking about an element like mercury that has very strong cohesive forces. And if we put mercury in a thermometer and we have it in that thin tube, right, we see the edge of that mercury going down. And that's because of cohesive forces to form this convex shape. Whereas if we have water in that thin tube, we observe the other, which is called adhesive forces. Adhesive forces between unlike molecules. And so what happens is the forces between the silica in the glass and the water are attractive. And so we end up having this concave shape here, where the water really likes to interact with the silica and it spreads out. And so we have this shape right here at the edge when water is in a thin tube. And we have this shape right here when mercury is in a thin tube. And that is because of the forces between the glass and the water. And cohesive forces exist because the mercury likes to hang out by itself away from the water. And so this line that I'm drawing here with the water and here with the mercury is called the meniscus. There's a page of practice problems that I'd like to also do in class. Okay, great. Hope that helps.